and which are affected by, can be affected by human activities. One of these gases is carbon dioxide. It's of course a very important constituent of the atmosphere. Together with plants, it creates organic material, which it also has created in the past the fossil fuel reserves on which our industry is nowadays running. Carbon dioxide has about a concentration in the atmosphere of 370 parts per million. And the amount is growing from year to year, roughly with about 0.4% per year, and has been doing this since the beginning of the industrial era, at the end of the 18th century. Carbon dioxide is important for climate also. It's a greenhouse gas, and an increase in the carbon dioxide content of the atmosphere will tend to warm the Earth's surface. It's a subject about which I cannot say much during this lecture. Other gases which are important, next one is methane, Ch4. It's produced in anaerobic conditions when organic matter is decaying. It's also produced from leaks in gas pipelines, in the production of oil and of natural gas. Its concentration in the atmosphere is 1.7 parts per million, and this gas, its concentrations in the atmosphere, was for a long time growing by about 0.5% per year. I have a good message now. For the first time this year, methane has not been increasing any longer in the atmosphere. We have reached an equilibrium between input of methane in the atmosphere and destruction by chemical reactions. And it might even be possible in the future to bring down the concentrations of methane in the atmosphere, which would have a favorable effect on the so-called greenhouse warming. It will lessen the greenhouse warming. Nitrous oxide is another gas which has concentrations in the atmosphere of 0.31 parts per million, less than that of methane, and it's a gas which continues growing in the atmosphere at the rate of about 0.25%. Its concentration in the atmosphere is about 0.31 parts per million. And then we have ozone. Ozone is a key component of our atmosphere. The chemistry of the atmosphere would be totally different if we would not have ozone in the atmosphere. And I cannot go into any details, but I can guarantee you that it is one of the most important gases which is in the atmosphere. It's consisting of 3 oxygen atoms, and it is produced from the photolysis of oxygen, O2, in the atmosphere, to which I soon will come. There are gases which even lower concentrations in the atmosphere, and these are, for instance, the CFC gases. And although their concentrations in the atmosphere are below 1 parts per billion, that's an American billion, that's 1,000 million, although the concentrations are much lower than that, the ozone destruction which have been observed in the stratosphere, and especially over the Antarctic in early springtime and early winter, early springtime, these low amounts of CFC gases are responsible for that. And my lecture will be very much about that topic. Under natural conditions, generally we can say ozone is mainly located in the stratosphere. The stratosphere is the layer of the atmosphere where temperatures don't any longer decrease with altitude. The temperature in the atmosphere is indicated by T in this curve. And once we reach the stratosphere, we see that temperatures are about constant with altitude. If you have conditions like this, then we have very stable conditions in the stratosphere, dynamically seen. It's very difficult to mix gases vertically in the atmosphere. So the ozone which is formed in the stratosphere by the photolysis of oxygen, that ozone is not easily transported downwards into the troposphere, and we should be happy for that, because if more ozone would come down from the stratosphere into the troposphere, we would have constant air pollution at the Earth's surface, even without the input by humankind. But we have this very favorable constellation in the atmosphere, in that most ozone which is produced in the stratosphere actually stays there, and only very little comes down into the troposphere. It was mentioned by one of my introducers that ozone is very important in filtering out ultraviolet radiation, and that is shown in this view graph. What is shown here is the depth to which solar radiation as a function of wavelength, here expressed in nanometer, penetrates down through the atmosphere. And you see that up to about 200 nanometer, most radiation coming from the sun is already absorbed above 50 kilometers altitude in the atmosphere. If there would be no ozone in the atmosphere, then the ultraviolet radiation between about 240 and 300 nanometer would come down to the Earth's surface. And this is very damaging radiation to the biosphere. So if there were no ozone in the stratosphere, and we only have about 3 millimeter on average of average ozone in the stratosphere, if there were no ozone in the stratosphere, life as we know it now is simply impossible. It's only in very hidden regions of the atmosphere where life could exist. When I started my studies on the chemistry of the stratosphere, it was believed that only 4 reactions played a role. And these reactions are shown in the right-hand side of this slide. It is the photolysis of oxygen, O2, by photons coming from the sun into 2 oxygen atoms, and each of these oxygen atoms recombines with oxygen molecules, O2, to create ozone, O3. If you add up these reactions together, you get out of 3 oxygen molecules, you get 2 ozone molecules. Now, if there were not reactions going the other way, back to oxygen, then within about 1,000 years, all oxygen in the atmosphere would be converted into ozone. And that would be a very poisonous atmosphere, which certainly doesn't allow for life on Earth, and certainly not for humans. So it's also very important that there are reactions going towards destroying ozone and reforming oxygen. And those are the reactions which are listed lower down. Ozone photolysis creates O atoms. Part of these O atoms react with ozone to make 2 molecular oxygen, or 2 molecules of oxygen, and as a net result, out of 2 ozone molecules, we form again 3 oxygen molecules. So the idea of Chapman was that the production of ozone by the first 2 reactions and the destruction of ozone by the latter 2 reactions would keep each other in balance, and that would explain the distribution of ozone in the atmosphere. However, it was discovered, especially in the latter part of the 60s, that if you just take these reactions as listed there and calculate the amount and distribution of ozone in the atmosphere, you get curves. These are the 2 curves most to the right in this figure, which actually indicate much larger concentrations in the atmosphere of ozone than was measured. The 2 curves to the left on this view graph. And that means that something else must also destroy ozone. Otherwise, otherwise we would have too much. We would calculate too much ozone in the stratosphere. And it turns out that these reactions, which are involved in ozone destruction, they can be influenced by human activities. In this view graph, I repeat again in the 2 first sets of reactions, the Chapman reactions, as invented by Sidney Chapman already in 1930. It was a very long time believed that these were the only reactions important until the end of the 60s, as I said. And the additional reactions which destroy ozone are listed under catalytic ozone destruction in this view graph. And you can summarize many sets of reactions which destroy ozone in a simple way. Say a molecule X reacts with ozone, making XO and O2. The ozone photolysis creates O atoms, the second reaction, and part of the O atoms reacts with XO, giving back X and O2. If you add up these three reactions, you get out of 2 ozone molecules 3 oxygen molecules. However, and that is like the Chapman reactions, they also do that. However, because of the catalytic action of a number of molecules in the atmosphere, which can be influenced by human activities, the speed of this reaction, creation of oxygen from ozone, is much faster than by the Chapman reaction. And these, that X can be nitric oxide, NO, in the stratosphere. You add NO to the stratosphere above 20 kilometers and you destroy additional ozone. Or X can be chlorine atoms, which come from the CFC gases. They contain chlorine, and when they go up in the stratosphere are photolysed by solar radiation to free the chlorine atoms which are part of the CFC molecules. Or X can be Br, and there are other examples. X can also be OH. And in this way, by being able to supply the stratosphere with catalysts, which nature did not make, or only in limited amount, we can destroy additional ozone. At least the nitrogen oxides are very important in destroying ozone by catalytic reaction was demonstrated to us very convincingly by a natural phenomenon, a so-called solar proton event. During a solar proton event, protons with high energy are spit out, you can say, from the sun, ejected from the sun. They reach the Earth atmosphere at high geomagnetic latitudes, above about 65 degrees, and there they produce nitrogen oxides, involving also fast electron production. So there are estimates showing that in a period of a few hours, the amount of NO, and this is the full drawn curves which are shown in this figure as a function of altitude, in a few hours times, in August 1972, large amounts of NO were produced, so that, for instance, at 40 kilometers, the amount of NO produced by the solar proton event equaled the amount of what you normally find in the stratosphere. So if ozone really destroys, if ozone is really destroyed by catalytic reactions involving the nitrogen oxides, we should expect that as a result of this solar proton event, at high geomagnetic latitudes, ozone should have gone down. And when I came on this idea, I called up NASA, the Space Research Organization in the United States, and asked them, have you ever seen a heavy ozone depletion around August 1972? And the answer was no, but the reason was they hadn't looked. Well, they started looking, and almost 2 years later, they confirmed this theory that ozone is destroyed by nitrogen oxide. What you see here on this curve is, as a function of altitude, the percentage ozone depletion about a week after the solar proton event, when additional NO was injected into the stratosphere. And you see a red curve going here, those are the observations, and you see a number of other curves indicating the percentage destruction as a function of altitude, which coincide very closely with the observations. There are a number of parameters which were not too well known when these calculations were made. And so we have a spread of possibilities, but you see that the observations which of ozone indeed very closely resemble of what theory predicts. Let me jump over this view graph. The CFC gases are brought into the atmosphere mainly at middle and high latitudes in the northern hemisphere. However, their lifetime in the atmosphere is very long. In the case of CFC11, that is in chemical form CFCl3, the lifetime in the atmosphere is about 50 years. In the case of CFC12, that is CF2Cl2, the lifetime is even 120 years. So these gases with such a long lifetime, they spread around the world. We have about as much CFC gases far into the southern hemisphere, in fact into the Antarctic, as we have in mid-latitudes in the northern hemisphere. That's because of the long lifetime of these gases. So they spread around horizontally, they also spread around vertically. And in fact, measurements made in Tasmania up to about almost 1987 or 1990 indicated a rise in the concentrations of CFC gases in the atmosphere by about 5% per year. That's a lot. Those gases were never produced by nature. And we can prove this by looking at the composition of air bubbles which are entrained in glacier ice at high latitudes. Air bubbles are, when glaciers form, air is enclosed. And these air bubbles, you can date them. They go back, even over Antarctica, you can go back 400,000 years and study the chemical history of the atmosphere for so long. These air bubbles showed that once you got below about at altitudes or deep down in the ice, which was formed more than 50 years ago, below that the CFC gases were not in the air bubbles. They were not produced by nature, and initially also not produced by mankind. The chemical production really started in the 1930s and accelerated after the Second World War. And this is true for a number of gases, and in particular also for the CFC gases. When the danger to the ozone layer by the CFC gases was proposed by my colleagues Mari Molina and Sherry Rowland, we started to study the case. This was still in the beginning of theory, and observations had to be made to confirm the theory. And some of these, and they had to be compared with model calculations in describing the vertical distribution of CFCl3 as shown in this view graph as a function of altitude. And what you see is a full drawn line, and you see a number of dots. The number of dots which are in this view graph are measurements, and the full drawn line indicates theory. And they agree very well with each other. So we were encouraged that we were on the right way, that we understood the chemistry of the stratosphere very well. And in fact, one thing I should say here, in this curve you see this decrease with altitude in the stratosphere above about 25 or 20 kilometers. That decrease is due to the photolysis of the CFC gases in the stratosphere. CFCl3 is photolyzed, and the chlorine atoms, which are hidden in the CFC gases, is then released into the stratosphere and destroys ozone. Also, one of the ozone killers, or the main ozone killer gas in the stratosphere, the CLO radical, CLO molecule, also that was measured as a function of altitude, and this is indicated again in this curve compared to model results, and even there you see that the correspondence is rather good. And so by the middle of the 1970s, we thought we understood the chemistry of the stratosphere very well. We calculated ozone depletions if we would continue to inject CFC gases in the atmosphere at a constant rate, as we did in the early 1970s. Then, with time, above about 25 or 30 kilometers, ozone would decline, say, until with amounts which in the year 2005 amounts to about 25% around 40 kilometers. And these calculations are even nowadays correct. This is indeed what happened and what has been observed. We are almost in the year 2005. At lower altitudes, where still we find most of the ozone in the stratosphere, below about 25 or 30 kilometers, we thought that not too much would happen to ozone. And one of the causes for that is that the ozone killers, CLO and NO2 radicals, they destroy ozone in these catalytic reactions which I showed you before, that they kill each other. They're like two mafia families which take care of each other. And in that way, both CLO and NO2, both ozone killers, are removed from the atmosphere. And also CLO radicals, again under the influence of reactions involving nitric oxide and actually methane, is converted in HCl. And chlorine nitrate and HCl do not react with ozone. So this is a good thing. This protects ozone from larger destruction, and we did not predict any changes in ozone below about 25 or 30 kilometers. Me also. And then we got a big surprise. In 1985, our colleagues from the British Antarctic Survey, Joe Farman and colleagues, presented the upper curve in this view graph, showing over their station, Halley Bay in the Antarctic, that total ozone in the vertical was going down very rapidly, and starting from about the middle or end of the 1970s. You know, you don't have to be a statistician to see that ozone is going down very rapidly. For a long time they did not believe their data because it was believed by everybody, the best scientists in the world, and and other scientists like me, that ozone was going down very rapidly. We did not expect that. This was impossible. All the textbooks said this ozone at these lower altitudes are rather, especially over Antarctica, are rather inert. You cannot do much to ozone. But finally the instruments were checked and other measurements were made, and it was found that ozone indeed was going down, and that we had a mystery. We had to explain this. And it turned out, in the left side of this view graph picture, I show you again the decline of total ozone as said before. I should say also what units are used here. When you see 300, that means about 3 millimeter of total ozone if you could contract all ozone in the stratosphere to standard temperature and pressure conditions at the Earth's surface. So it's a very thin layer of ozone which protects us from ultraviolet radiation. And we see from these measurements over Halley Bay that between about the middle of the early 70s and 1985, that ozone was being halved, reduced by 50%. And where did this ozone depletion take place? If we now look at the right-hand curve, then we see that the ozone depletion took place just in the altitude region, where normally, and this was for instance in August, the 15th of August, where normally we find a maximum in ozone, just exactly where normally, without chlorine gases in the stratosphere, ozone was measured, maximum ozone was measured, and before springtime, late winter and springtime, we have high amounts of ozone, maximum ozone. A few weeks later or a month later, that ozone is gone, and we have zero ozone just in the same altitude region. This was just crazy. I mean, how can a thing like that happen? The worst conditions the furthest away from where the CFC gases are released in the atmosphere. So initially we had no explanation for it. And theories were developed. Some theories were very innovative, rather funny. We have also, but of course the scientific quality was not too great. I must also say that some of the scientific proposals which were made to explain the ozone hole were of the same quality, unfortunately. But through very intensive studies by scientists in Europe and the United States, we got together the explanation for the phenomenon. And what it turned out is that wonderful clouds, which occasionally under very cold temperature conditions form in the stratosphere at high latitudes, especially in the Antarctic, that these wonderful colored clouds, so-called mother-of-pearl clouds, which are formed between 10 and 25 kilometers in the stratosphere, that these wonderful clouds become very dangerous if by any chance there is too much chlorine in the stratosphere. And this is due to human activities. The reason for that is the following. This view graph I show you here is a little complicated, but let me say it in simple words. When temperatures are low enough in the stratosphere, below minus 80 degrees Celsius, when we get conditions like that, what happens is that the nitrogen oxides and chlorine nitrate and HCl basically are removed from the stratosphere. Firstly, the nitrogen oxides are converted into nitric acid, and nitric acid together with water vapor freezes out in so-called nitric acid trihydrate particles, crystal particles, forming very small very small size particulate matter in the stratosphere, basically ice particles, but involving nitric acid. On the surface, in that way, NOx, NO and NO2 are removed from the stratosphere. And that by itself makes the chlorine mafia very happy, because they are on their own and can gobble up ozone. But not only that, on the surface of these ice particles, and this is listed on the point C in this curve, chlorine nitrate and HCl, the compounds which normally in the gas phase do not react with each other or anything else, those compounds react with each other to make, on the surface of these ice particles, not in the gas phase, there they don't react, but on the surface of ice particles they react, they form Cl2 and nitric acid. The nitric acid freezes out again, and if sunlight returns to the stratosphere after the long polar winter, then Cl2 is photolyzed into two chlorine atoms, and these chlorine atoms, and that is listed lowest down in this view graph, enter a catalytic chain of reactions involving Cl, ClO, and Cl2O2 as catalysts, which again transform ozone into oxygen. And what is important to notice here is that the speed of this reaction cycle, which destroys ozone, is through the second reaction, depending on the amount of ClO, of ozone killers, in the stratosphere to the second power. Now, I showed you before that chlorine was increasing in the stratosphere by 5% per year. That means that the destruction rate of ozone in the stratosphere goes up by 10% per year. And when ozone starts going down, it goes down more and more rapidly. This was confirmed by measurements on a high-flying research aircraft by our colleagues, American colleagues. They found that at latitudes polewards of about 68 degrees Celsius, where temperatures are very low, about below minus 80 degrees Celsius, that exactly in those regions the amount of CLO radicals grew very much compared to normal conditions, and if that happens, then ozone is going down, and this is clearly shown on the right hand side of these figures. You see that the full drawn curve, which is ozone, goes down from about 2.5 parts per million to less than half of this amount, and if the measurements would have been taken later, then ozone would have been going down. At the same time, CLO radical concentration has risen very steeply in the region once we entered minus 80 degrees Celsius. There are many factors which come together. Not only is the atmosphere very sensitive to the amount of chlorine in the stratosphere, but once ozone is being depleted, it gets even colder in the stratosphere, because ozone in the stratosphere warms the stratosphere to some extent. If there's no ozone, it gets colder. If it's getting colder, then more ice particles are formed, more chlorine is being activated into the Cl and ClO forms, and more ozone is destroyed. So you have another reinforcing condition here, which really creates this sort of catastrophe. Under natural conditions, chlorine is supplied to the stratosphere only in very low amounts in the form of methyl chloride in CH3Cl, and that is the white sector in this bar graph. But if you look at the chlorine content brought about by other gases, industrial gases in the atmosphere, including CFC11 and CFC12, but also carbon tetrachloride, methyl chloroform, and a few other chlorine-containing gases, you see that, in fact, we have now 6 times more chlorine in the stratosphere than was ever supplied by nature. And that means that the speed of the reactions which break down ozone in the stratosphere through ozone in the stratosphere by chlorine catalysis, that has gone up by 6 times 6, at least 6 times 6, that's 36 times compared to natural conditions. So under natural conditions, chlorine does not play much of a role in the stratospheric chemistry, but through the additions of chlorine by human activities, we have a speeding up of the catalytic destruction by a factor of about, say, 36 to 50. And that means that once ozone is going down, then things get worse from year to year, and this is exemplified by these figures where we look down on the Antarctic region. These are satellite measurements showing the total amount of ozone in vertical direction over Antarctica, and you see a steady development from October to 1980 to, on the left upper part of these globes, to October 1990, to the right on the lower part. You see the change in color to violet, and that means ozone amounts which are of the order of only 100 Dobson units. We have lost 2/3 of the ozone over Antarctica compared to natural conditions. And this all happens within a very short time period, in a time period of only a few weeks, by the addition of very small amounts of chlorine to the stratosphere. We have learned this, and it was not predicted. The area in which ozone depletion takes place also has grown. In 1980 there was hardly any depletion, or the area of lower ozone was very limited. It was not noticed, but with time it grew, and in 1998 or so, the area over which the ozone hole had developed over Antarctica was much larger. It was about of the size of the North America, even more than the size of the Antarctic continent. If we would have really carefully looking at the data, we could have seen that already in 1981 over Antarctica there was some depletion of ozone. I don't have a pointer here, but you see there was a bite out already in the ozone profile in 1981, and that grew with time. So indicating the very rapid development. Once things get bad, they get worse from year to year. And although the ozone hole was discovered in 1985, and that is shown in the upper curve again, these were the measurements from our British colleagues. In further years, as long as the CFC gases kept rising in the atmosphere, ozone was being depleted further and further, so we could reach these very low levels of about 100 Dobson units in the atmosphere. Over Antarctica, these conditions, very low temperatures, last over a long period of time. You see at about minus 80 degrees Celsius, this is the vertical scale on the left, you see a line, horizontal line going, that it's the line indicating the temperature in which polar stratospheric clouds or these mother-of-pearl clouds can be formed. And normally in the stratosphere, that's the blue curve, temperature over Antarctica, temperatures are below those lines. So there's a very long period starting from the end of May until the middle of October, when temperatures in the stratosphere over Antarctica are such that polar stratospheric clouds or nitric acid trihydrate particles can be formed, and ozone depletion can take place. Over the Arctic, this is fortunately by far less prevalent. We have conditions there in which it's basically largely in the month of January and in February when ozone depletion can take place. And because sunlight is also essential for ozone depletion, and in January we don't still have such much sunlight over the Arctic, the ozone depletion is much less prevalent than over Antarctica. But there are some years when things also at northern latitudes, over North Polar regions, can show rapid ozone depletions, and that is shown in the left-hand curve. We have again the ozone hole over Antarctica. On the right, in the right-hand curve, we see measurements from Finland, from 67 degrees north, indicating in the blue curve normal conditions, and in some years, and this was the case in 1997, in some years, the red colors, 1996, we see that there was much less ozone than in other years. Those were years when temperatures were cold enough also over the Arctic over a longer period than normally, in which ozone could then be destroyed. So we also had minor cases of ozone holes over the Arctic regions. We skip some because of the loss of ozone in the stratosphere. The penetration of solar radiation to the Earth's surface increased very strongly, and that is shown in this curve showing measurements, the lower curve of the flux of photons around 300 nanometer in at the Earth's surface over Antarctica. That's the full drawn curve. That was for the year 1988, and the ozone hole was not as deep as in 1990. That's the other points to the left and upwards from the full drawn curve. They indicate the levels of ultraviolet radiation in the year 1990, when there was much less ozone, protecting ozone over the Antarctic. And that means, if you look at the left-hand scale, logarithmic scale, that over in the year 1990, the penetration of dangerous ultraviolet radiation around 300 nanometer to the Earth's surface was increased by roughly a factor of 10 compared to 1988. And it's just around around 300 nanometer that the sensitivity of biological material for ultraviolet radiation rises very strongly towards shorter wavelengths in the atmosphere. Here demonstrated by some bacteria, but you could also show similar curves for human erythema or for plankton. Very similar behavior. That means that the risk of sunburn, not only at high northern and southern latitudes, but also at mid to high latitudes in other parts of the year, that the risk for sunburns and other effects of ultraviolet radiation were the largest had increased until recently, and averaged over the whole globe and the seasons. We have, for instance, in the southern hemisphere and to a somewhat lesser degree in the northern hemisphere, we have increased ultraviolet radiation by of the order of 4%, which is something to take serious. And it has been taken seriously, and some of the effects are here summarized according to a study by the United Nations Environmental Programme, UNEP. Uvb effects. In humans, we worry about increase in cataracts. There are estimates that per 1% ozone depletion you get an increase in cataracts by about 0.6%. That means, translated globally, 100,000 more blind people per 1% ozone loss. And also there's an increase in the risk of non-melanoma skin cancer by 3% per 1% depletion in ozone. Land plants, about 50% of the land plants show negative effects due to increased UVB radiation, less growth and smaller leaves. For some agricultural plants, for 1% decrease in yield, there will be per 1% depletion in ozone, there will be a 1% decrease in yield for some agricultural plants. And also marine ecology can be harmed by additional or large increases in ozone in the decreases of ozone in the stratosphere. So international measures have now been taken since 1996. The industrial countries in the world do no longer produce CFCs or methylchloroform or halons. These are bromine-containing compounds. Bromine is more dangerous than chlorine. I come maybe back to that at the end of this lecture rather soon. These compounds, which harm the ozone layer, are no longer produced in industrial countries, and in developing countries they will be out of production in a few years' time. The replacement products, HCFCs, are allowed until the year 2020. The replacement products are like the CFC gases. However, one of the chlorine atoms is replaced by a hydrogen atom. And if that is the case, then the compounds become much more chemically labile. They can be removed in the troposphere by reaction with hydroxyl radicals, with OH. And that means for the same amount of input of CFC gases in the atmosphere, HCFCs, the replacement products, would only be about 5% as dangerous as the original CFC gases. Methyl bromide will probably be regulated, but it's still being discussed. But the plans are around 2005 to phase out the emissions of methyl bromide in the atmosphere. Altogether, it's going to be better, but it will take some 40, maybe 50 years until most of the ozone hole will have filled up again, because the lifetimes of the CFC gases in the atmosphere are of the order of 50 to 100 years. So it takes a long time before they are reduced in the atmosphere by the action of solar radiation in the stratosphere. There is, however, a worry that it may take longer, and the reason for that is that carbon dioxide which is a greenhouse gas, so more carbon dioxide in the future will warm the Earth's surface and the lower atmosphere, that same carbon dioxide in the stratosphere will lead to cooling of the stratosphere. And that means more ice particle formation and more chlorine activation, extended chlorine activation, and that in turn will lead to more ozone depletion. So maybe this estimate that the ozone hole will be gone by the middle of this century maybe is a little over optimistic, but we have to see further. Um, we already are seeing that the amount of chlorine in the troposphere, that's close down to the ground, has already passed its maximum. Its maximum concentrations of tropospheric CF chlorine provided by the freons, the CFC 11, 12, and 113 gases, that has maximized already around 1995, and we see this very slow decline in concentrations of chlorine in the stratosphere, in the troposphere. In the stratosphere it takes a little longer because it takes time before the CFC gases can be lifted in the atmosphere into stratospheric altitudes. So with regard to the stratosphere, we are now about at the time when we have reached maximum levels of chlorine in the stratosphere. So from now on, very slowly, we will return to more normal conditions. But from time to time, this recovery, which will take a long time, will be disturbed by very bad years when the temperatures in the stratosphere just stay at very low values. And that is unpredictable. That's dependent on the meteorology of in the stratosphere also, and you know how unpredictable weather can be. The effect of the agreements to phase out the CFC gases is very drastic. In the upper part of this curve, you see various curves. If no regulations had been issued on the production of CFC gases, if there were no protocol, Montreal Protocol, then the amount of chlorine would have been rising very rapidly in the atmosphere, reaching by the middle of the next century concentrations of the order of 20 parts per billion in the atmosphere, about 8 times larger than actually nowadays is found in the stratosphere. So it is very, very good that measures are taken. The initial measures was the so-called Montreal Protocol. In the Montreal Protocol, it was agreed upon to bring down the production of CFC gases by a factor of 2. But you still see that the amount of chlorine in the stratosphere kept rising because the emissions are, even on these amounts, are still larger than can be broken down by photochemical reactions in the stratosphere. Even the London Agreement, which was a further strengthening of the regulations, even that would have led to a further increase of ultraviolet radiation, of CFCs in the stratosphere and ultraviolet radiation. First, through further agreements in Montreal, we have reached a situation in which we gradually return to normal conditions. However, if you look at the lower part of this curve, it's about at that time when the ozone hole will have gone that we also have reached the largest effects on excess skin cancer cases in the atmosphere. Because on top of the slow removal of the CFC gases from the stratosphere, the effects of the solar radiation on causing skin cancer in human beings is delayed. You don't get easily skin cancer when you're young, but when you are 60 or 70, that's the time when you are punished for lying in the sun and doing sun bathing when you were 20. So we have these long delay factors indicating that with regard to the effects of CFC gases on ozone, we haven't reached the maximum. Still further increases are expected. We see that we are now looking at various gases in the stratosphere. We already indicated some gases which are listed here. We see a slow return to normal conditions. In other cases, the amounts of gases increases with time. We have the scales, I hope you can read them. These gases which increase further in the atmosphere, these are the replacement products for the CFC gases. And they are adding something to ozone depletion, although by far not as badly as the CFC gases would have done. Finally, let me say let me tell you something about a nightmare which I had, a scientific nightmare, not a real nightmare. And that this concerns bromine. Bromine, on a molecule per molecule level, bromine is about 100 times more effective in destroying ozone than chlorine is. So one can ask the question, what would have happened if the chemical industry, instead of producing chlorine-containing halocarbons, had produced bromine-containing halocarbons? Or also, we can say it in other words, at the beginning of the 70s, when we started to discover these, when we were not yet aware of the danger of these gases in the atmosphere, we knew very little about their chemistry. For the same money, the chemistry of chlorine could have behaved the same as the chemistry of bromine. We didn't know that. If that would have been the case, we would have rushed into very dangerous situations already by the middle of the 1970s. Already by the middle of the 1970s, ozone would have been depleted everywhere, not only at high latitudes, but everywhere by a factor of 2, by the action of the bromine gases in the atmosphere. And that is because bromine, in comparison to the chlorine gases, bromine is, much of it is always available in this very aggressive form, in the form of Br atoms, BRO radicals, and molecules like HOBr. And they enter into catalytic destruction reactions, which are very rapid. So we are just very lucky that we never entered into a situation like that. But it was certainly not because we were so wise, or chemical industry, or we scientists were so wise. We're just very lucky that chlorine needed ice particles to become very active. If it had been bromine, they don't need the ice particles. They are largely in the activated form. So, what does this teach us? Well, we should also, in the future, we should very much stay, we should continue to be involved in research. For each molecule, or each compound which are put into the atmosphere, also in waters, let us be very careful at looking what are the consequences. The ozone hole was totally unpredicted. Our science was not good enough. Our science is maybe never good enough, but we should at least try always to be able to predict some of the worst consequences. Another thing we have learned is that things were actually much worse than we initially believed. Roland and Molina predicted ozone depletion above 30 kilometers. But the very large ozone depletions which took place at lower altitudes, they were not predicted. They were measured first. We saw the ozone hole and needed an explanation. And that means that we must continue making measurements, because our theories may never be really enough developed to be sure that we make the right predictions. And of course, a very important lesson is that we have seen that a part of the atmosphere, in a chemical sense, became unstable. We had a runaway effect developed at high latitudes in the northern, to some extent in the southern hemisphere. And if you look at if you consider another issue, and that is of global warming, by the increase of carbon dioxide in the atmosphere, chemically and physically and biologically, a much more complex issue, then you ask yourself, is it possible that this climate regime, or parts of it, will enter under very unstable conditions? I'm saying this, there are some examples of things which might happen. We cannot prove it, but we should occasionally look for worst case situations. And here I would like to finish, and I hope for a vivid discussion. Very nice talking to you. Thank you.
you put on the light, please? I would like to open the floor for questions and discussion. And please introduce yourself before asking the questions. And I would request it to be very brief and to the point so that we have more people from the floor can get a chance to discuss their point of issues. Yes.
Professor, I'm really feeling myself very fortunate that I could listen to your talk. My name is Sadananda. I'm a professor of computer science. I am not a chemist. My knowledge about chemistry is very meager. I just would like to ask you, although you mentioned about the Antarctic area's ozone depletion and also mentioned the Arctic area, but most of the attention is only on the Antarctic region. Most of the human actions are in the northern hemisphere, isn't it? Why is it that there is not so much talk about the Arctic ocean, except one slide I saw where you mentioned about it? And I'm curious to know about it. Thank you, sir.
So if I understand correctly, your question is, why is especially Antarctic so much affected by human activities?
Not the other side. There is no human activity.
Yeah. Well, this had to do with, it doesn't really matter anymore. If you have gases with very long lifetimes in the atmosphere, they get by transport in the atmosphere by winds and by turbulence, they get everywhere. So you have about as much CFC gases in the northern hemisphere as in the southern hemisphere, as in the tropics. There's not much difference. The same is true for the stratosphere. So that the action of the CFC gases is the concentration, so to say, at various altitudes is about the same. And then if there are special conditions arising in the stratosphere over Antarctic, like low temperatures and sunlight, if these conditions are fulfilled, together with the chlorine, which is transported everywhere, then you run into these very unstable chemical conditions, in which during a period of about 3 weeks, a maximum in ozone concentrations, just there exactly, is converted into a minimum, into the ozone hole situation, between 12 and 22 kilometers altitude.
Hello? Please switch on the microphone.
Thank you, Dr. Crutzen. In the introduction, they mentioned that you were studying the effects of high-altitude aircraft. Could you share some of your findings with us about that? And the other question that I have, my understanding is that ultraviolet radiation produces ozone. So as it increases the NO2, doesn't it also increase the ozone itself, especially where the hole would open and the radiation would penetrate deeper into the atmosphere? Wouldn't that create more ozone?
Yeah, those are good questions. To some extent you do that, but the effect is very small. By reducing ozone, indeed, ultraviolet radiation is coming down further downwards into the atmosphere. However, ozone is formed by the photolysis of oxygen, of O2, at short wavelength, very short wavelength, below 240 nanometers. So, while the ozone destruction reactions are formed by ultraviolet radiation up to much higher wavelength. And that means that the ozone depletion reactions also are increased, and actually more than the increase in production of ozone. So these factors are overriding each other with the longer wavelengths finally taking over and causing more ozone depletion. That's one of your, does that, high-flying aircraft? Yeah. Then I have to tell you something about the very complex role of nitric oxide in the atmosphere. You probably are very well aware that nitrogen oxides at low altitudes near the ground, together with the emissions of hydrocarbons and together with sunlight, produces ozone by photochemical smoke reactions. In the stratosphere, this is also the case up to altitudes of about 20, up to 25 kilometers. Above that, ozone is being depleted by the catalytic chain of reactions, second or third view graph which I showed you. So it's a question of where the aircraft flies. If they fly below 20 kilometers, they tend to make more ozone, basically by the photochemical smoke reactions. If they fly at higher altitudes, then they destroy ozone. Now, the aircraft which have been flying at lower altitudes than 20 kilometers. So we have never seen an ozone depletion. We have seen a small, we have even seen, our models show a small ozone increase in the stratosphere. In reality, this has, however, never happened because the only supersonic aircraft which would fly at high altitudes, they are no longer in business. The Concorde has been withdrawn from operation.
Yes, any more questions?
Professor Crutzen, my name is Chongnak Professor from Thailand. I am a water engineer. I like to thank you very much for the excellent presentation, and you give us some optimistic hope that in the next 40-50 years, perhaps the ozone layer will be better. But this week or recent months, we have heard about some discussion about the Kyoto Protocol, which you did not mention anything about Kyoto Protocol. And there are some superpower nations that show no interest or no commitment to follow the Kyoto Protocol. If that is the case, what are your prediction or estimate? Would that have effect on ozone layer? I mean, greenhouse gases. Can you say a few words on this matter? Thank you.
Yeah, I cannot give you exact numbers, but the effect of increasing carbon dioxide in the atmosphere has the secondary effect that the lower stratosphere from about 17 kilometers upwards will cool and increase and promote the formation of ice particles. And ice particles, as I showed, are very dangerous if there's enough chlorine, if too much chlorine in the stratosphere. So the recovery of ozone may be further delayed. In some estimates, we might have to wait on the end of this century. We cannot give a definitive answer. It depends on some properties of these particles and very much also on how much carbon dioxide is added to the stratosphere the rest of this century. It's the two countries, by the way, which are not signing the protocol of Kyoto. Those are the only two superpowers still having nuclear weapons in an oversupply. They're not behaving as they should.
Yes, any more questions? Yes, please.
Yes, could you address the other chlorines, other than just CFCs? Aren't the other chlorines also dangerous?
Yes, and the main compounds we have to worry about were the CFCs, but also carbon tetrachloride, methyl chloride, but that is largely natural, not totally, because it's also produced by biomass burning. And we have a number of other chlorine-containing compounds like C2, F2, F2Cl4, and etc. There's a whole battery of gases which were emitted in the atmosphere, but in lesser amounts than the CFCs, but the consequences are very similar. But what I showed you is really an addition not only of the CFC 11 and 12, but also the other chlorine-containing gases.
The chlorine we're using for water purification, swimming pools, and all of that.
Yeah, well, those chlorine gases which are produced that way, they are not in, except maybe chloroform. They are not. They're not in organic form. They're mostly in inorganic forms. They are removed from the atmosphere much more effectively by rainfall, by being taken up in cloud particles and then being removed by precipitation processes.
Thank you.
Thank you very much for your very interesting presentation. I'm Lette Mieke Mulder and I'm here this week to participate in a workshop on sustainability. And there we also address some of the more, let's say, softer sides of science. And what we can learn from the experience on ozone is, well, first of all, that there is a gap between there are scientific findings and facts and the time that actually there is some political and other action. And on ozone, we were probably lucky because there were some clear things we could do. On some of the other issues, and I'm thinking in particular about global warming, the actions are perhaps, or the issue is perhaps much more complex. And I wondered whether you would have some recommendations and perhaps learnings based on your ozone experience that you could give to, let's say, the non-scientific community.
Well, you ask a very important question, which is very difficult to answer, because basically we know what has to be done to improve the things in the climate warming issue. We know what has to be done. But the fight is about whether it will harm economies of some nations or not. And some nations just say that they're not going to take to follow the Kyoto Protocol because they think it harms their industry, their economic output. Other nations are of a different opinion. In Europe, we are a little better, not much better, because we are only reducing the emissions of carbon dioxide in the atmosphere compared to 1990. In the year 2012 by only 5 or maybe 8%. It's still peanuts. In order to stabilize CO2 in the atmosphere, you have to reduce the total emissions of carbon dioxide into the atmosphere by at least 60%. And if you want to reach such conditions, then you see the monumentous task we have ahead to get into this situation. And think, in reality, this cannot be achieved. We have unfortunately to live with the prediction that carbon dioxide will continue to grow in the atmosphere. But we should try to limit the growth as much as possible to prevent the worst things from happening. I cannot say much more than that. Some governments listen to us and me. Other governments just don't do that. But things will change. You can be an optimist, you can be a pessimist. Sometimes I have the feeling nothing will happen before some climate hole, we can call it, situation. Instead of an ozone hole, an instability in the climate system will develop. When that does, then maybe there will be quick action. But like was the case for the CFCs. But there is no easy solution, and we should continue to put pressure on governments, but everybody of us also singularly should do whatever he or she can to alleviate the problem. I mean, if you look at the development, the many cars, around the world. Now Asia is filling its roads with so-called environmentally friendly German cars. And you see the crazy situation. It's good for the economy of Germany, maybe, but not for the world. So the attitude, political attitude, has to change. I cannot really, but really I cannot answer your good question.
Yes, any more question? Yes, please.
This is regarding your last slide. My name is Rakshit from AIT Bioprocess Technology. My understanding is that the chemistry labs, we normally handle bromine compounds much more carefully than chlorine. So you are suggesting that it was a bit of a luck, but what I'm trying to get out from you is that it's more because people don't use it because of its high corrosive nature. Is that true, or was it luck all the way?
Well, the chemical properties of the chlorine-containing compounds were more friendly than of the bromine-containing compounds. That's why the industry went into production of the chlorine-containing compounds. But then you can turn the story around. We didn't know anything about the chemistry, or not much about the chemistry of chlorine in the atmosphere. And by the same token, chlorine chemistry might have behaved as bromine chemistry. We didn't know from the beginning. If that had been the case, then we would have had catastrophic developments already by the middle of the 70s, when we did not have the instrumentation available to measure these highly reactive compounds in the stratosphere. And the theories had not been developed. With environmentally friendly cars, especially German cars.
Well, I think we have more opportunity to discuss with him informally after we conclude this session and have a reception in the dining hall. So at this point in time, I would like to invite our registrar, Professor Gautamaria, to give a vote of thanks.
The votes of thanks can be very brief. We can simply say thank you, Professor Paul Crutzen. But I shall take a little opportunity here to express my feeling after listening to his lecture. I didn't capture much the beginning of the lecture because it seems to be quite technical, but I think I captured the later part when you talk about how lucky we were, for instance, not to have used bromide, but also to have a scientist like yourself to help predict the effect of those CFC, and also lucky that we have successful protocol, maybe because the non-production of CFC did not affect much of the world economy, but anyhow we were so lucky. But on the other hand, I felt somehow unlucky when you said that it needs at least 40 more years, and when you say that 10,000 or 100,000 blind per 1% increase of the or loss of the ozone or whatever, and many more cancers are to be predicted. And with this, the cause and effects are not immediate. It takes so many years, and it should bring us more caution in our own behavior. But most importantly, I think Professor Crutzen has shown us a model of human striving for a better understanding of our environment. And also, as a scientist, he has shown that scientific endeavor is together with social responsibility. It is a scientific responsibility to give facts, a very well researched analysis, and warning to decision makers that what they are doing may have a very catastrophic effects if we are not be enough cautious in our work. And I think AIT is an institution where we always say that our mission is to develop highly qualified and competent professionals for sustainable development of the region. And then I think all of us should follow the example of our guest speaker today. I would like to thank all of you and would like to invite all of you to express our great appreciation to Professor Paul Crutzen. Thank you very much. May I invite Professor Mario Tabucadon to give a plaque of appreciation to our speaker. And I would like to announce that today is a very special day for Professor Paul Crutzen. If I'm not mistaken, he's exactly 70 years old today. So, as a token of appreciation, we have some little thing to show you now.
It's a pleasure that Professor Crutzen is celebrating his birthday with all of us. Let's wish him a very, very happy birthday. Happy birthday to you. All of you are invited to a piece of this cake in the dining hall now. No, dining hall.